Yeah, good. Thank you, everyone. Shambhavi, please go ahead and introduce the speaker.
Sure. So, hello everyone. Today we have with us Dr. Samarth. He is a postdoctoral researcher at Intelligent System Labs at Intel in Santa Clara, California, USA. Previously, he was a PhD student at Georgia Tech, and he has interned at NVIDIA and Facebook Reality Labs. His areas of interest include computer vision and machine learning research related to grasping. So today we are going to discuss his paper Hand Object Contact During Grasping, which was a paper published by him in ECCV 2020. We welcome you, sir.
Yeah, please go ahead, Samarth. Please go ahead.
Okay, thank you. And yeah, so actually, I thought I would discuss not just one paper, but kind of a line of work which
Yes.
involves three papers. But I'll try to um have a combined theme out of all of them.
Yeah. Go ahead. There's no time limit as such. You please take your time and cover it in depth.
Yeah, sure. Okay, so let's start. So, as I said, this is a collection of three papers, and in general, my research interest is in what is called functional grasping, and uh, that means grasping objects, but not just for the sake of grasping, but to do something with those objects after you have grasped them. Um, and that could be either how observing how humans do it or replicating that through robotics. So a big line of my work is in this field where we are trying to observe how humans do this. Um, and even within grasping specifically, I focused on the contact that happens between hand and object during grasping. And then, as I said, kind of a parallel line of work is trying to recreate this human behavior through robotic grasping. Okay, so the main high level motivation is, of course, as a computer vision researcher, you want to be able to understand images and videos uh, better, right? And even if you look at just this one image, it tells you a lot. It tells you not just that someone is holding a camera, but also that they intend to take a picture, right? Uh, and so understanding hands in action, it's kind of been a long-term goal for computer vision scientists. Uh, but one part that has been missing, I believe, is contact. So here, contact between finger and the button over there is what tells you that they want to take a picture. And so that's kind of what I'm exploring, that I've explored in my thesis. And so contact is very important for all of our physical interactions, right? With objects, with other people, although that is a little bit discouraged these days, but in general, uh, with robots as well in the future. Um, and if we were able to have very accurate understanding and modeling of hand object contact, what could we do? For example, we could design better robotic hands. So here I'm showing an example of a soft robotic hand. Now, when you are designing this, you probably want that robotic hand to be able to achieve the same kinds of contact that the human achieves. Um, because we've designed all the objects and surfaces around the world to fit with our hands. So that's one application, potential application. It, contact modeling is also very important in making virtual reality experiences more realistic. Um, so, for example, in virtual reality, what it's happening is it's looking at your hands in the real world and trying to recreate them in the virtual world. But if you don't have really good contact modeling, then everything will look fake. And more realistic contact modeling makes it look more engaging. Uh, and the same with uh, same with robotics, right? So as I'll show later also, it can really help with robotic grasping and making robots that assist humans. So let's see. So yeah, I mentioned the importance of contact modeling, but also that it hasn't been done a lot before. And the reason is observing contact is difficult, right? I mean, even if you just keep looking at this image, uh, the actual surface of the finger that's in contact with the camera is occluded. Like you can't actually see that particular surface. And you can you can take a model-based approach to try to solve that. So for example, you have a 3D model of the camera, and then you have a 3D model of the hand. And then you might say that I will just look at where the 3D model of the hand is very close to the 3D model of the camera. But currently we are not able to model the very complex human hand to the level of detail necessary to be able to do that. And that too just from a single image, right? So collecting contact data has traditionally been very difficult, and maybe that's why uh, it hasn't uh, it hasn't taken a lot of research space yet. And uh, so first thing we thought when we were trying to decide a PhD project was how can we actually capture contact. Now we know that when contact happens between hand and object or hand and any surface, we know that there's some pressure that's exerted by the hand on the other surface. And probably more important from my research perspective is that heat is transferred. So we know that in solids, the rate of heat transfer is uh, is the highest through conduction rather than convection and radiation, right? And so here I'm showing you side by side two examples. So on the right, it's a pressure image from a sensor morph, which is a planar pressure sensor, and it kind of gives you as an output a pressure image. And I should mention that this sensor is kind of one of the highest resolution sensors available for pressure sensing. And on the left, I'm showing you a thermal image. And what actually happens is the hand is put on any surface, basically some kind of plastic surface, and you hold it for a few seconds, and then you take away the hand. And after you've taken away the hand, you look at that surface through the thermal camera, and the thermal camera gives you this thermal image. So you can see clearly the difference between the two. The thermal image has a much higher spatial resolution. So this is basically on the order of 160 by 120 pixels on the pressure image, whereas thermal sensors are much more developed. So you can get 640 pixels by 480 pixels. It's much higher spatial resolution. You can imagine that it works for arbitrary surface shapes, whereas the pressure image is dependent on the shape of the pressure sensing surface. And it's much harder to make that into any random shape. Most of the pressure sensors are planar, or if they are deformable, then they have their own problems. And another advantage of using thermal imaging is that it is kind of non-invasive in the sense that you don't need to instrument whichever part of your environment you want to capture contact. You don't need to instrument that with these expensive pressure sensors. You don't need to stick pressure sensors everywhere. You just need to have a thermal camera and look at the world, and it will reveal this contact to you. Uh, on the pressure image side, one advantage is that it focuses more directly on the quantity that we're interested in, right? We're interested in the contact pressure, uh, also to a little extent contact location. So, but the relationship between the thermal pixel values and the contact pressure or contact location is kind of indirect. But I will come back to that later. So with that background, I just want to present the first paper in this line of work, which is called Contact DB, which is where we kind of formalized and introduced this whole notion of using thermal cameras. So before that, as I said, people have worked a little bit on contact capture. So for example, you can do 3D reconstruction of the object surface, like what I'm showing here, and then simultaneously you can determine where the hand is, and then you can say the points on the surface where the hand is close to the surface. I will just say that those are contacted points. But that's kind of an indirect inference rather than directly observing the contact. So it's susceptible to errors in this 3D reconstruction of the surface, also susceptible to errors in the hand modeling. Another example is using these kind of tactile gloves. So these are gloves, inside them you have these pressure sensitive surfaces. And that is kind of a different sensing approach because it captures contact on the hand rather than the object. Um, and all these bulky gloves and things like that can influence natural grasping behavior, which we want to capture full natural behavior rather than some kind of influenced behavior. And there have been some other approaches in the computer vision community. For example, they compute this contact separately in some kind of simulator, and then given an image, they kind of retrieve the closest simulation using features from this image, and then they say, this is my guess of contact. So it's kind of like a nearest neighbor approach, but also it has obvious limitations in accuracy. And then there has also been some work on crowdsourcing. So Amazon Mechanical Turk. So people have presented these kinds of 3D models of objects, and they are asked to select points on the object which they would prefer to touch to do something with the object. So that is kind of like this kind of saliency. They call it tactile mesh saliency, which is very different from the kind of data that we are able to collect, which is very much kind of directly related to the actual contact that is happening. So you can see some examples here. For example, if you compare the wine glass here against some of the objects, like this cup or something, you can imagine, or they have the wine glass here as well. You can see the difference between the two. Okay. So as I said, the main idea is very simple, using this heat transfer, right? And we observe that heat on the object surface using the FLIR boson thermal camera. And that is kind of rigidly attached to this Kinect RGBD camera, which gives us RGB, so color image, and depth image. And then the thermal camera gives us the thermal image. And we decided to 3D print the objects in our dataset rather than using real world objects for a couple of reasons. One is that the 3D printed objects, they all made of the same material, so they have the same thermal properties, whereas different real world materials have different properties. We actually tried this idea on many different materials, and it works for a vast majority of materials. Like it works on plastics, glass, wood, cloth. It works on all of them, but not on metals, because metals are really good conductors of heat, and the moment you take your hand away, the heat that you left on the object surface, it just gets dissipated very quickly. But even within the materials that it works, uh, it has different rates of diffusion based on the material properties, and we wanted to standardize that. So we choose this 3D printing. And also it has the advantage of we know exactly the 3D model that we use to print this object. So that will help us downstream, as I'll mention in a later slide.
One question, Samarth. What was the material used for the 3D printing this thing?
Yeah, the material is called PLA.
Okay.
I think it's polyurethane something. I don't know the
Okay.
full,
Okay.
but it's kind of the standard material that's used
For all.
in all the 3D printers. Yeah,
Okay.
yeah.
Good. Thank you.
It's some kind of plastic. Yeah.
Yeah. Yeah.
And so here I'm just want to show you this. Uh, so just this is a video of this object which has been grasped and it's rotating on the turntable. This is the depth image from the Kinect, and side by side this is the thermal image that we capture. So you can see really here this kind of contact information that is hidden from our eyes, but it's kind of revealed very nicely with the thermal camera. And this is the effect that we will use to capture contact.
And
So
how long does that remain there? The
yeah,
heat.
that's a good question. I have that in a couple of slides. It's
Oh,
coming up. Uh, this is just like the set of objects that we use for the data set. So it's a mixture of real world objects like glass or eyeglasses, hammer, knife, that kind of thing, and some abstract shapes at different sizes. So we have pyramids and cubes and spheres. Uh, yeah, and then some other kind of funny objects like the hand. Uh, so here, yeah, so this probably answers the question that you had, which is how long does this kind of imprint last? So I'm showing 0 seconds after contact, 18 seconds, 35 seconds. So yeah, it starts dissipating, but within about 15 seconds, the dissipation is very small. So if we are able to scan the object within those 15 seconds, then it's fine.
okay. Good.
Um, and this shows, maybe I'll come back to this image later. But first, I wanted to mention this. So how we actually do it is, so we have this object which has been grasped and then put on this turntable, and then the turntable is rotating. While it's rotating, we capture these RGB depth and thermal kind of three images at different points as it is rotating. And at each instant, uh, what we do is we use this depth image and the 3D model of the object that we have to fit the 3D model in this depth image using using ICP and simple things like that. What that does, it gives us the 6D pose of the object in this with respect to the camera, right? So it tells us exactly how far the object is and what is the angle of the object. Once we have that, what we can do is we can take these pixels from the thermal image and kind of project them onto the 3D model of the object, right? According to the pose that we know. And since it's rotating, we observe it from all the different angles. So then finally we get kind of this coherent uh, contact information on the 3D model of the object, which is called texture mapping. And so this 3D model of the object textured with these thermal images is what we call contact maps. So in the data set, we had data from 50 participants. So we invited them to our lab and they were grasping all these objects. Uh, in total, we had this set of 50 objects, but out of them, 27 objects were grasped with the intention of using them. And then a superset of 48 objects were grasped with the intention of also handing them off. So in total, we have about 4,000 contact maps. Uh, so here is an example of this contact map, for this kind of game controller. But you can go to this website, contactdb.cc.gatech.edu, where like basically you can explore the entire data set and even download it. So you can click on all these different objects. You can select the participant from 1 to 50, use or hand off, and then it'll load this model, and you can see how the contact is, and you can also download all that data. So some analysis that we did, I'll quickly go through that, and I'll also speed up a little bit. So the functional intent that I mentioned, use or handoff, really significantly influences the contact. The size of the hand also influences. The larger the hand, people prefer, so people with smaller hands prefer bimanual grasps. Um, and kind of an interesting question is how much of the contact actually happens at the fingertips rather than other areas of the hand. So uh, we kind of had a rough analysis of that. So what we did is we used we kind of annotated the fingertip area of the different participants, and then computed a upper bound on what the maximum fingertip, if they were touching all their fingertips, what would the maximal contact area be, and that is indicated by this red line. And then we compare that against these blue bars, which are the actual full hand contact area that we observed on the whole object surface. And we see that the blue bars are often higher. So that means that a lot of contact is actually happening. Um, a lot of contact is happening at non-fingertip areas as well. So I think there's a question. How
Yeah,
was
yeah,
the
yeah.
annotation
Yeah, I just
done
wanted
with
to
the fingertip?
curious. How did you do it?
Yeah. So I mean, uh, I'm missing that slide here, but basically before each, when each participant arrived, we kind of got a contact print of their hand on a flat plate. It's just
Okay,
their whole palm on a flat plate.
okay,
And in that you can see the fingertips clearly
yes,
and you can mark them.
okay, okay, okay.
Uh, that's how you can get this fingertip area.
So one is enough, right? For one individual, if you do it once, it's fine.
Yeah, yeah.
Okay.
So actually, we kind of did it for 5 or 6 people, and just averaged the contact area. So this is like the average fingertip contact area.
Oh,
That's maximum possible. If the average person was touching all of their fingertips, this would be the contact area.
okay.
Uh, Now, so that's an interesting thing because a lot of the grasping software and robotic software, they model contact as a single point per fingertip. Uh, and that's we are arguing that that is not capturing the entire process of grasping. A lot of contact is happening at different areas as well. And so that's a motivation for kind of changing that. So I'll quickly also show some results on predicting contact, these kind of contact maps from the object shape. Uh, and the problem is interesting because it's a one-to-many problem, right? For the same object, so the same object shape, we have many correct ways of grasping it. So each participant grasps it is kind of a different correct way of grasping that object. And that is different from normal machine learning where it's a one-to-one mapping. And I think in the interest of time, I will skip the actual method, but um, you can refer to the paper. Here I'm just showing you some results, mainly to highlight that this is a hard task, and the results actually not look very good because you can see that it captures like the overall gist. So these are objects that it has never seen before. So it was trained on a few sets of objects, and then this mug, pan, wine glass, it has never seen these objects before. Uh, and it's trying to predict the contact for using the object. So you can see that for using the mug, it either kind of contacts on the body or on the handle, or for using the pan, it contacts on the handle. Similarly for the wine glass, but it's not as crisp and as detailed as the kind of the ground truth that we have. Because this is a hard task, this one-to-many mapping makes it a particularly difficult problem. And we will come back to this task in the next, in the third paper that I'm going to talk about. Uh, I'll skip this for now. Now, I mentioned that I'm also interested in the robotics side. So this paper is probably more focused on the robotics side. Um, and so here what's happening is we are trying to use the contact data that we have to try and create robotic grasps, similar to how the humans did that. So as you might know, there has recently been a lot of progress in robotic grasping. So I'm mentioning just some representative examples here. So, um, but that progress has mostly been focused on bin picking kind of tasks. Uh, so bin picking kind of task is where you have objects in a bin and then you just want to sort of randomly pick objects from that bin and transfer them to some another bin. And uh, using very simple parallel jaw grippers, so which is just a kind of a gripper that can open and close at the end of
Mm.
the robot. Now there are many things about this kind of particular problem uh, which makes it possible to collect lots and lots of data automatically, because you can do what you can do is you can just randomly try to pick things from this bin, just automatically randomly, and then by chance if you manage to grasp something, then you can label that as a successful attempt and all others are unsuccessful attempts, and you can create this large data set and train from that. But as I mentioned, a lot of the grasping that humans do is very different. It's not like just randomly holding objects. We are holding objects in a particular way, uh, and the hand is also very different from this kind of parallel jaw simple gripper.
Yes.
Uh, and so the progress in that kind of robotics has been a little slow, mainly because I mean the robotic hands are also just becoming more and more complex. It was really hard to create human-like hands before, uh, and because of that, all the downstream tasks have been also delayed. So here, I want to highlight some papers that have attempted this. So, for example, this paper, what they do is they collect data from a human expert by having them wear these kinds of gloves, and then the human grasps objects, and then they have this complicated transformation function, which is called I forget the name, but it's called basically a transformation function between the space of the human hand and the space of the robotic hand, right? Because the shape is slightly different, how the joints are arranged is slightly different. So then they have this transformation function which transforms the human demonstration into the robot space, and then the robot can learn from that demonstration. Uh, what we are proposing is that, but that transformation function is really hard to construct. What we are proposing is to get demonstrations from human beings in the contact space, not the hand configuration space. So in the contact space, basically this contact map serves as the demonstrations from the humans. So this is saying that the human contacted this object here. So now my robot hand should try to recreate that contact as much as possible. And if it is able to recreate that contact faithfully, then that means the grasp must have been correct. I should also mention that that is a little bit of a simplification, because aside from the contact location, what is also important is contact forces that are applied. And this paper does not deal with contact forces, but I believe that it's a step in the right direction. So just quickly, the problem definition is that someone gives us an object 3D model, so which we call object geometry, and then a contact demonstration from the human being. And then we want to develop this algorithm which can generate these kinds of configurations of various hands. So they can be, for example, we have this model of the human hand or a model of this robotic hand, many different robotic hands. And we want to generate grasps which are similar, which try to recreate the contact that we observed So how we do that? We have this very simple contact model, which just kind of randomly samples points from the object surface. And if those points have been contacted in the human demonstration, then they are marked as attractive, which is green, and then others are marked as repulsive, which is red. And then we have these three kind of example uh, hand models or end effectors that we did our experiments with. So they have 20 joints for the human, 16 joints for this Allegro robot, or 4 joints for this Barrett robot. And the process that happens is kind of simple. So I mentioned the attractive and repulsive points before. So here they're showed in red and green respectively. And what happens is there is an optimization with different cost terms. So the first one is it's trying to attract the from the green point, all the green points are trying to attract the closest part of the hand towards themselves. So like attraction is happening everywhere here. And then all the red points are trying to repel away any part of the hand that are close to them. So there's repulsion going on here. And then there is a term which discourages intersection of the hand inside the object, because we know that hand cannot go inside the object. So there are these different terms, and then the optimization procedure tries to optimize the various joints. So all these joints of the hand are kind of variables, and those variables are being optimized so that this attraction, repulsion, and intersection are correct. So, and there's also a term on the thumb. So we know that humans always have their thumb on the object while grasping. So we're just trying to encourage that. So here's a video which shows that in action. So you can see that the joints are being arranged so that, you know, the repulsion happens and the attraction happens, and the penetration or intersection is discouraged.
So which software was this? Which software was used to model this?
So it's mentioned in our paper. It's basically called DART. It's dynamic articulated real-time tracking.
Okay, okay.
And the code for that is also available
Good,
publicly.
good.
Now the main part is that this optimization is very local, and it can only work if the starting point is kind of close to what you want, right? So if the hand is just very far away or in a very different position, it won't work. So to get a good initialization, what we need is uh, what we do is we sample lots and lots of grasps using this grasp it, which is another grasp uh, like another grasp modeling software, and we just randomly sample lots and lots of different grasps. So you can see that over here. And once we have so I should mention, to encourage diversity in all these randomly sampled grasps, what we do is we initialize that with many different approach points, you know, all over the object surface, and then approach directions. So, you know, rotation around the approach vector, and then the approach distance as well. So all of these initial conditions, from each of these initial conditions, we start that grasping software, and for each of them, we get a few final grasps, and all of them are collected. So all of them are collected. So here I'm just showing a 3D model, and then we use GraphIt to have all these different randomly sampled graphs. Now someone gives us this contact map, which is a demonstration from a human about how a human contacts it. And what we do is we use again the software Dart to do that optimization. But the optimization is started at all of these different starting points, right? In the hope that one of those starting points will be close enough and it will converge this optimization. So um, that's how this whole process happens. And then once we do this, this Dart software also reports whether the grasp has converged or not. So we can see uh, it kind of gives us a number which indicates the, the convergence, and so we can sort by that number so that the correct grasp is at the top of the sorting list. And so here are just some results of using the hammer with different kind of models of the different robotic hand models, and handing off the hammer again with different hand models. And it also fails in some cases. So for example, if the human demonstration is that my finger should go through these holes in the scissors, and the sampling uh, is not exhaustive enough, then it's not able to converge to that particular complex grasp. Or also, if the hand is just too simple to grasp the object in a complex manner, then it can't do that. For example, for mouse, we would like to place a finger on the button, but with this kind of very simple robotic hand, it's not very possible to do that. Okay, so there was a second paper, and I just want to come back to that possible applications that I talked about. All of this soft robotics, realistic VR experiences, all of that. So those were good applications to keep in mind. Um, but for all of these applications, what we really need is models of the contact. So in the first paper, we just showed how you can capture contact, but now we need a model of the contact between the hand and the object, right? So what we need is someone gives us a configuration of the hand and the configuration of the object, and we would like to know very precisely how the hand is contacting the object. That's what we mean by contact modeling. So like someone gives us, let's say someone gives us this state of the cup and state of the hand, but we need to know exactly which points on the cup are being contacted. Or even more difficult, if it's the human hand, then the human hand is actually kind of soft and deformable, right? And so it's very unclear how the hand is kind of deforming, and then it's touching it, and then it kind of flattens out as you apply more force, and then it's touching various points on the object. But the good news is we are able to know exactly where the contact happened from the thermal imaging. What we are missing is the hand part. So just want to highlight some current work in that. So in computer vision, there has been some work on 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 basically like hand pose estimation during grasping, but it kind of largely either ignores the contact or kind of treats contact as a second or as a consequence of the grasp uh, rather than as important as the grasp. So what they do is they have the object state, and then they have the hand state, and then they say, okay, I will intersect the object with the hand, and wherever it intersects, that is the contact. Um, in virtual reality software and in simulation software, as I said before, contact is often modeled as a single point per fingertip. And I mentioned before how that is not capturing the full picture of the contact. But I should just mention that there's a kind of related line of work in human whole body pose estimation from images, where they're starting to look at whole body contact rather than just for example, some points on the object, on some points on the body. So for example, this paper, they look at contact happening at all of these blue areas uh, to say that, okay, to have a really correct and consistent body pose estimate consistent with the world. So this new paper that I want to present, in that we collect data uh, that's called contact pose, and that has high resolution contact as we had before. So I'm showing you this contact maps here. But in addition to that, we have these 3D hand joints, which I'm showing here. Left hand in red, right hand in green. or sorry, right hand in red, left hand in green. And along with those 3D joints, we also have these 3D mesh models of the hand, and we also have that data. And along with all of that 3D data, we have image data in the form of these RGB, and we also have depth images, which I'm not showing here, but along, and all of that 3D information can be projected into these RGBD images. So it kind of collects a lot of different modalities of data that are useful for this kind of research. So this data set that enables a rigorous study of contact modeling by collecting in one place all of these different modalities. So we have all these 3D object models, we have the RGBD images showing the grasps, and then we have the contact ground truth, and then we have the hand and object pose ground truth. And then we also have some machine learning experiments about doing this contact modeling. So we use the same kind of setup to capture the contact, as I mentioned before. And we have these 3D printed objects. Now they are blue, but the setup, the contact process is a little bit, sorry, yeah. The capture setup is a little bit different now. So now we also want to track the object and the human hand and things like that. So we have this kind of frame, and then these 7 different cameras which are going to track the object. And I'm going to show that later on, how the tracking is done. And then we have these 3 Kinects instead of the 1 Kinect that we had before. And that was because so that we can see the person from many different points of view. And I think there's a question. So
Swaroop, you can unmute yourself
yes.
and go ahead. Swaroop.
Yeah. This in the previous slide where you said you're using the hand pose also along with the contact map. So
Yeah.
at the end, you have actually created a data set. So is it that you're going to you're going to provide this data set and try that robot simulates the same thing? Like, because the joints and all, according to what you said, are different in the human and the robot. So are you trying to replicate human kind of structure in the robotic grasp? Is that what is an application of the asset?
Yeah, that could be an application of this data set. We haven't done that yet. We haven't
Maybe
done that yet.
Swaroop, like, are you asking like how will the robot perceive the object with this data set, or how will it use? Is that the question?
Yeah, maybe that is also
Yeah.
one
So
point.
I mean, I think basically I mentioned this before, right? I mean, for robotics, the question also is in which space you should try to replicate. Should you try to replicate in that hand pose space, or in the contact space, or maybe you have both of them? And I think there is a lot of good things to be done in replicating in the contact space. Replicating in the hand joint space uh, has been done quite extensively before, and we've seen that it works to a certain extent, but after that it has its limitations, right? So I think the purpose of collecting this data set was more to study this contact modeling rather than robotics. It was more of a computer vision data set rather than a robotics data set. But it has the data that you need if you want to do robotics with it. So we have the contact maps, and then as a baseline, if you want to, compare against, if you want to kind of create a transformation function by yourself from the human hand to your particular robot that you have, and you want to compare that as a baseline, then we have this data as well. So it's kind of a place that collects all of this information in one space, in
Okay.
one place, and then you can use that however you want to.
So that is maybe further research point which could be done,
Yeah.
correct?
Yeah. Yeah.
Will you discuss future work, Samarth, at the end? Any quick
If
point?
we have time, yes.
Yeah,
If
yeah,
we
yeah.
have time, yes.
Yes, yes. Please go ahead.
Yeah. So we have these three Kinects, as I was saying, and then again the thermal camera, which is over here, and that's looking at the turntable, where after grasping the object is put on this turntable. So one important limitation that I should mention of this whole approach is that the grasping that needs to be done is kind of static grasping, right? So if if there's a lot of kind of different grasps happening on the same object, then all of that will introduce many different thermal prints on the object surface, and then it becomes complicated to distinguish which grasp presented which print. So what we instruct the participants is to grasp the object once and then hold it steady in their hands. It's kind of what is called static grasping. Um, so what happens is, so again, there are these participants which we invite to a lab, and they stand in this frame. They're holding the object, and then they're just kind of moving it randomly inside this space. And while they are moving it, we are capturing data from the three different kinects, and we are using this software called OpenPose to detect the hand joint locations. I mean, that detects all the joint locations of the body, but we are most interested in the hand joint locations, as you can see here. Now, those joint locations, each of them individually are a little bit noisy, but what we can do is we can use 3D geometry to triangulate the 3D joints from the 2D observations from all these different images, right? Uh, so once we do that triangulation, a lot of the noise is canceled out, and I'm showing that triangulated 3D joints projected back into the image. Uh, Along with the object. The object is being tracked using these OptiTrack cameras, and it's being shown using these green dots on the object surface. And what those green dots are these markers. So to track the object, uh, we explored many different possibilities. Um, so here, the important thing is we don't want again to kind of interfere with natural grasping behavior. So we have, for example, if you have these markers that are kind of protruding from the object surface, then people might want to avoid touching them, or people might want to specifically touch those kind of protruding markers. To avoid that, what we did is, while 3D printing, we introduced kind of small cylindrical recesses in the surface so that the marker can be put inside, and it's kind of flush with the object surface. So you can see that here. And given that, so that allows us to track the object by tracking these markers. But at the same time, it's interfering very less with the natural grasping behavior. So using that whole process, we can get the contact maps, as I mentioned before, and the hand joints. And these are just some examples. So again, we see the functional intents really influences how people grasp objects. Uh, and then we have single-handed grasp, we have bimanual grasp. I think this is one of the few data sets which has bimanual grasp data. A lot of the data sets out there just have single-handed grasps. Um, and again, this time we have a set of 25 objects instead of 50. So we have about 2,300 contact maps. But the main thing here is now we have almost 3 million RGBD images showing the grasps. And we have all those hand pose data as well. So some related work. So compared to a lot of the related work, the kind of compromise and data that we provide is that we provide uh, these RGBD images of the graphs, we provide the hand pose, we provide the object pose, and we provide the contact. And all of it is largely markerless, because these markers, you can't really see them in the RGBD images because they're so small. And I think that's a unique kind of intersection of data that is different from all the other related works out there. Now, these hand mesh models. So you might be aware of these um, mesh models called nano mesh models. So they are kind of configurable 3D models of the human hand. And how they are configured is you can change these two variables. There's the hand pose and hand shape and hand pose. So hand pose is basically just like all these joint angles, the angles of the various joints on the hand. And the hand shape is shape of the hand. So like how large the hand is are the fingers fat or thin, all those kind of different variations. And what this model provides is that uh, given a particular hand shape and hand pose, it gives you, using this J function, it gives you the 3D joints of that particular hand. And what we do is we optimize this beta and theta over here, such that the joints for that particular beta and theta are close to the 3D joints that we have from our data sets. So it's simple enough. Uh, and then there's another term which kind of prevents this hand shape from getting some unnatural values, like very thin or very, very fat. So, so then using that procedure, we are able to kind of configure these 3D hand models into the data that we have. So I'm showing some examples here. And then I'll skip this slide. And then what we can do, which we were not able to do before. So before we just had the contact maps, and those were just kind of yes, yes or no, like does contact happen or not. But here we are able to associate the contact regions with different parts of the hand. So here the white areas are non-contacted and the colorful areas are contacted. But even within the colorful areas, we're able to say that this area was closest to the middle finger. So we know that that contact happened from the middle finger, or from the fingertip, or the next phalange or the previous phalange, things like that. So in short, we're able to associate each contact area with the area of the hand that created the contact. And from that, we are able to look at the probability of contact for different areas of the hand. And we see that like average over the entire data set, how do people contact their hands with different objects. And we see that it's biased towards the fingertips, but a lot of contact actually happens at the non-fingertip areas as well, which confirms what we saw before. And we also see that some fingers are much more important from the contact point of view than some other fingers. So if you have, for example, if you're designing a robotic hand yourself, you might want to consider just having a three-fingered hand, because all of the contact or most of the contact that humans perform is captured within these three fingers and the thumb. You might not even need a little finger. Um, and then we are able to do what we call active area discovery. So what that means is, for example, this flashlight, right? So we have we know all the various hand configurations of grasping the flashlight, and we also know which points were contacted on the flashlight using the contact maps. So we can say out of that we can filter out the points which were touched by the tip of the thumb, and filter out all the other contacted points. And averaging that over the entire data set, we see that most people place their thumb at the button of the flashlight, right? Um, and this has an interesting application in this COVID era, a potential application. So for example, as you're reopening various buildings and things like that, uh, you want to discourage contact, right, between
Yes,
between
yes.
different people. And
Yeah.
so, but at the same time, there are various areas in buildings which many people are contacting.
Yes, yes, yes.
And those areas you want to sanitize more frequently. You don't.
Yes,
It's very costly to sanitize the whole building. So if you want to
yes.
focus on particular areas, which areas should you focus? Now, if you have a thermal camera looking at the whole room, and
Mm-hmm.
you look at data from, let's say, 24 hours or 1 week or something,
Mm.
then these kind of active areas will emerge out, uh, based on, where people touch more frequently, because those areas will continuously have more and more heat transfer from the hand to the surface. And then if you're able to kind of isolate these active areas, then you know which areas to sanitize more frequently.
Does
Um,
distance matter? Distance, thermal camera distance, because I have seen most of them close range. So if
yeah,
we have to cover a room, it'll be
yeah,
tough.
yeah.
Mm.
Yeah, I mean, you need a different camera, but the good news is the thermal camera technology is very well developed. So
Mhm.
they have thermal cameras with high focal length and
Mhm.
high large field of view,
Mhm.
which can look at a larger area as well.
Okay, okay.
Okay, so let me skip this slide. So coming to the contact modeling part, which is kind of machine learning part. So again, as I mentioned before, the what we're interested in is this kind of very uh, kind of small, low level problem where we are given this object shape. So here, for example, it's given in the shape of a point cloud, in the form of a point cloud, and then we are given some information about the hand. So we are either given this hand skeleton, uh, or we are given the hand mesh model. And from both of this information, we want to train a machine learning model which can give us where exactly the contact happened. And it's important to have this, not just single point on the object surface, but we really need this precise contact information, so that all those downstream applications can use that precise contact information. uh, so what we do is, using this hand shape and the object shape, we extract some features, right? We extract some features for each point on this point cloud, for each of the endpoints. And then we use, off-the-shelf machine learning technique, which operates on this point cloud to
Yeah.
predict contact value.
I had one question.
Um,
How did you generate this point cloud?
yeah, so we have this 3D model of the object, right?
Mhm.
Blue
Mhm.
thing.
Mhm.
Um, and from that, you like using, um, I think, yeah, you can use Mesh Lab, or you can use PyMesh, or there are lots of other softwares
Okay.
which can sample points on the surface of any
Mhm.
3D model. So that's just like sampling of the surface.
Yeah, yeah. Because I've seen this in LiDAR data, 3D point cloud. So I was just
Yeah,
curious how you did it. Okay, good, good.
yeah. LiDAR also gives you point cloud. That's
Yeah,
true.
yeah, 3D point cloud.
Um,
Yes.
yeah. So now these features, we tried various different features. So simplest one is, you know, you just look, which you call simple joints, which is just the uh, which is just using for each point. So basically, we want to calculate features for each point on the object, right? So uh, you can have just the 3D location of the joints of the fingers, which is the simple joints. For relative joints, instead of the 3D locations, it's calculating relative vectors from the object point to the joints on the hand. For skeleton, as I mentioned, we can make a skeleton by connecting these joints, and then we can have a vector from the object point to the closest point on the skeleton rather than the joint. And the skeleton introduces information about connectivity of the joints, right? So, for example, we know that these two joints, even though they are nearby, they are not connected by any finger or anything, but these two joints are connected. Uh, and then the mesh, which uses the kind of the 3D mesh model of the finger, that one is computing a vector from the object point to the surface of the mesh. Um, think I will skip this contact representation slide in the interest of time.
Yeah.
And another interesting thing is you might think that a very simple baseline is what we call proximity heuristic. So what you can do is you just have the surface of the object and you have the surface of the hand, right? And then you just see where the hand is proximal to the object surface, and you say that that is where the contact happens. So we have that as a baseline that we compare against. But I just want to show you the kind of the result from our machine learning contact prediction. So you can see that given this skeleton, it's able to predict this high resolution contact values, and like these black parts of the hand indicates that the features for those parts have been zeroed out to kind of simulate imperfect hand pose, but it's able to reason about it, and it's able to kind of still say that there is contact happening there based on the hand pose and contact of the other fingers. We also did this.
You had mentioned about threshold, proximity threshold. What does that mean in the paper?
Yeah, so what this means is that, okay, so let's look at this example here, right? So you decide a threshold on the distance between the distance between the here it's showing two different hands, but you can imagine an object and a hand as well. So let's say there's an object and there's the hand. You decide and you can compute distance between points on the object and points on the hand, right? And you decide a threshold, let's say 2 millimeters or something, and you say that if the point on the hand is less than 2 millimeters away from the point on the object, then I will predict that contact happened here. Otherwise, I will predict that contact did not happen. Yeah.
Shouldn't it be 0 when there's contact? There's no distance at all, right?
Yeah, ideally it should be 0, but that is the problem with these kinds of proximity methods, is that
some margin.
you are not able. You need some margin because there are modeling errors in the hand and there are modeling errors in the object and things like that.
Understood.
And it's very difficult to select a good margin, and that's the whole problem. That's why we need this machine learning. Yeah.
Yes.
And we can also do the same thing with images, right? So I mentioned that we have these grasping images. What I've done here is I've extracted the hand and the object, and then kind of just put random backgrounds from image data set in the background to blank out the green background that we had. And then what we can do is we can use a convolutional neural network to extract some features for each point in this image, right? And then we do this 3D aggregation. What that means is we use the pose of the object that we know, and we use the camera focal length and things like that, which is called camera intrinsics, to project these features. So you can imagine the 3D model of the object is kind of in this image, and you're projecting features from each of the pixel onto the visible part of the 3D model, right? And then from various perspectives, you're doing the projection so that you cover the entire surface of the point cloud. And now that you have these features of the point cloud, then you can use the same point net to do the contact prediction.
Yeah, the camera intrinsics in an image, do we get it from the raw data? The raw file that we get, does it have that intrinsics information?
I think some of the raw files have that, or you can have it separately. So there's a whole procedure for calibrating the camera using a chessboard. And then it's very simple to do. And once you calibrate that, you can get the focal length and center, focal center, everything. Yeah.
Oh, good.
So yeah, like here's the result. So these are the 3 images that we used as input, and then the contact model outputs this contact prediction. So quantitative results, I think Yeah, so this what I wanted to mention. This gray line here is that proximity heuristic that I mentioned before, and that is good enough. But I think with machine learning, we are able to achieve even better performance. Like for example, you see this mesh, the options with the mesh features that are able to
Mhm.
outperform that significantly. And again, if you there's a new website contactpost.cc.caltech.edu, but if you go to that website, you can again kind of check out this entire data set, and you can download all the data and all the code for using the data set and things like that. Um, and here's just an example. Lots of different graphs that are present in the data set. Uh, Images with the 3D information projected inside them from the three different kinects. So second kinect, um, and then the third kinect. Uh, yeah, and I also had this thing about pressure, but I think I will skip that.
Yeah, yeah.
Yeah, and I think all of this information, if you want to find more, read the papers or download the data, you can go to this my website, and all of this information is there.
Good, good. Very good, Samarth. Very good.
Yeah.
Yeah, before we have some questions, but before we move on, during your defense, this is part of your PhD work, right? I believe. Yeah.
Yes.
So during the defense, did they ask any specific questions or any key points that they touched upon during the defense?
I mean, yeah, there were lots of questions. Probably something. One question I remember was about these hand models, right? So I talked about various ways of representing the hand, the skeleton or the mesh and things like that. And one of the questions was, all those are kind of derived from computer graphics perspective.
Mm-hmm.
Uh, Now, if you want to kind of design a hand model from a robotics perspective,
Mm-hmm.
which is more contact aware or things like that, how would you design that particular contact model?
Mm-hmm.
Sorry, particular hand model. Um, and I think there were some other questions too. Yeah.
Very good, very good. So in VR, how is it done? How do they create the model in VR?
I think every company has their own proprietary hand model.
Mm.
Uh, but it's some variation of this kind of articulated 3D mesh. So
Mhm.
it's it's like a mesh representation of the hand, and then you give it some parameters,
Mhm.
and according to those parameters, it will change itself, and you can change it. Now in VR, there's an important constraint, which is it should be power efficient. It like you can't use like a very complicated hand model because you
Mhm.
need to do it at 30 or 60 frames per second, right?
Yes, yes, yes,
Um,
yes, yes.
so there's always a trade-off between how accurately you can model the hand
Mhm.
and uh, how
Yeah.
power efficient it is.
Mhm.
So people are trying to find. Now in VR, right now most of the hand models are not kind of contact aware. More
Okay.
at most, what they're doing is if you have the controller that comes with the VR headset, they're able to, if you press a button on that controller, they can
Mm.
kind of snap the finger to that button because
Oh,
they know that the button was pressed, so contact must have happened. But
understood.
if you look at hand grasping some other arbitrary object which they don't know about, then the contact is kind of not very realistic. Uh,
Very good.
but they're all trying to make improvements. So
Yeah.
yeah.
Yeah. One more question I had is now we are depending on the thermal camera for ground truth, I believe, right? So, how accurate is the thermal camera? Like, for example, if you take multiple thermal images from two different cameras, or is
Yeah,
there any error? So, we are depending on that information, right? So, how accurate
yeah.
is that information?
It depends on the quality of the thermal camera. I think there are some, you might have seen some handheld thermal cameras, which
Yes,
I
yes,
guess they
yes,
use
yes,
outside stores and things like
yes,
that.
yes, yes.
those are kind of very specific single point. They measure thermal at like maybe a very small area.
Yeah.
So that's a different characteristic. Now, if you want to look at kind of cameras which give you thermal image, then there are some cameras which you can mount on your mobile phone, and those are very low resolution, like 100 pixels or 200 pixels. But we use this other one, which is slightly more expensive, but it's a separate thermal camera, and it has a higher resolution, 640 pixels by 480 pixels. But in terms of accuracy of the temperature that they measure, uh, I think they come with their own data sheets, and you can look at that. Here, what we are interested in is not the absolute pressure. Like, we don't want to know that it's 39.2555 Celsius. What we want to know is just relatively relative to the object surface. Is it hotter or not? So,
Got it.
Yeah.
So you don't need that accuracy.
Yeah.
One more question I had was, how did you integrate this thermal camera data into your work? Because that format will be different, and how did you integrate that information?
So, I mean, as thermal cameras improve, their interface technology also improves. So, before you used to have thermal cameras, and then you need a special hardware called a frame grabber to get the thermal camera, the data from there. But these days, you can kind of buy these cameras, which are just like webcams. So they have a USB port, and you can plug them into USB.
Okay.
And it's just like a normal webcam.
So it's like
that becomes
you take
very
30
easy
frames.
to integrate.
You can
Yeah.
set the frame rate. Okay, it's just like a normal video, just like a normal
Yeah.
video. Okay.
Yeah.
One last question: how did you differentiate between right and left hand in your this thing? How was that done?
So if you remember, there was that software that I mentioned, OpenPose.
Yeah.
Which detects the 2D, which detects the key joint locations in the 2D images of the Kinect. And that software is able to give you left, right also.
Okay.
And in some cases, I manually said that this is left hand, this is right hand. So based on a combination of that.
Good. Thank you very much, Samarth. Very incredible work. Very good. So probably now you can just talk about how you got into robotics. That's what Shambhavi was asking. So Shambhavi, so you can just talk about that.
Sir, I had one last question. Yeah. So, the left and right hand part, as sir was talking. So actually, it also depends, right? Sometimes the contact differs between the right hand is a bit stronger than the left hand. Was that also used as a factor in modeling your contact thing, the data set?
No, we did not do that, but I think that's a really good point. Let me see if I can bring up that slide. Just 1 second.
Okay. Let me make it easier. Yes, I think you can share again.
Yeah.
Very interesting what Samarth contact pose. Very interesting.
Yeah. So this thing, so as I mentioned, we are primarily interested in contact location and not contact force. I think what you were mentioning about one hand being stronger might have more effect on the actual forces that people apply. And I think
also
that's
I guess it also has an effect on the thermal image, right? Because like maybe the higher the pressure, the longer the contact, maybe more heat transfer.
Yeah, that's true. And some of the slides that I skipped, we are trying to predict pressure from the thermal image, but that's something that has not been published yet. But in that, we did observe that left and right hand have very different characteristics. So I think that is a very valid point. And left right difference also, how that shows up here is in terms of just preference. A lot of people prefer to use their right hand more. So you can see that, like contact is more distributed on the right hand. Sorry, no, this is for use and handoff, so maybe not very relevant. But we saw that, a lot of people use their right hand more frequently than left hand. Yeah.
And also one more thing, this data set you've modeled under special conditions and all that, right? You've not used, neither have you used the natural objects or natural light. So
Yeah.
how well would this generalize if we are training a robot or something for the grasping purpose? So how well would it generalize maybe? Any trials on that have happened or something like that?
Yeah, no, that's a good question. And I think at some point you need to make different compromises for different kinds of data that you want to capture. So here we wanted to capture contact, which was very important for us. And so for that, it was important to use the 3D printed objects and not real objects. Um, the reason why 3D printed objects, I believe that 3D printed objects can still generalize potentially, is you also have depth data, and in the depth data, what only shows up is the shape of the object, right?
Yeah.
So, and while doing the 3D print, we're selecting the models. We kind of selected realistic shapes, and they're at realistic sizes of the objects. So, if you train something on depth data, that has a higher chances of generalization. For RGB data, I think, yeah, you're right that the objects are all, single texture, blue texture. But I think, if you, there are two things. One is the object itself, and the other one is the background. The background can be randomized, as I showed in one of the slides, by just using some random backgrounds and segmenting the hand and the object. For the object itself, yeah, I think that's a drawback of the data set. But on the other hand, it allows you to train models for contact, which is much harder to do with any of the real object data sets. So it's just what you're more interested in.
A
Yeah.
trade-off.
So, Samarth,
Yeah.
in any of the application where we know what are the objects that you are dealing with, I think in those cases they should be fine, right? Because we already know what we are dealing with. In applications where it is defined what objects will be dealt with, I think this should be pretty good, right? This should apply pretty good.
Yeah, and you can also do other things, like you can put artificial textures on the because we have these high quality 3D mesh models of the objects, right? You can put realistic textures on them, and then maybe you can project them onto the image, something like that. But we haven't tried that.
Good. Very good work, Samarth. Spectacular work. Yeah, so much. Great that you could share it.